Hi class. Okay, so now we're getting into two more optimization problems I'm going to work through with you. These are higher level difficulty because of the functions that have to be created. You can see I already have one set up. This is one of the functions we'll be creating. So yeah, buckle up your seatbelts. It's going to be fun. So these are both from your textbook. And I just wanted to work out for you so you can see the logic, and hopefully just seeing more examples will help you as you continue to optimize. So here we have this trapezoidal drainage gutter, okay, and it's going to be made so that the angles are 120 degrees at the cross section. So that is, right here. So this is not at all to scale. I just grabbed a trapezoid image of the internet. So that means this would be 120 degrees. I realize that that doesn't look like 120 degrees, but okay. Actually, maybe it does. So the 5-meter long sheet metal, okay, it's being bent to form an open-topped gutter, and the width of the sheet metal is 60 centimeters. Okay, so that means that it's 5 meters long. So this here is 5 meters, or 500 centimeters. But the width, so this DA to AB to BC is 60. Okay, so when it was just a sheet, this was 60 and it's being bent up. So now we want to determine the cross-sectional area that will be a maximum. So we have to come up with an area for this trapezoid that's only in one variable that allows us then to find the derivative and maximize it. So what we are trying to maximize cross-sectional area. So it's the area function we need to create. So let's get to work on doing that. So let's label some of these points. So we'll call this dotted line H. That's the height of the trapezoid. Then we'll say that these two sides, which must be equal, are both X, and we'll call this base Y. Okay, so we know that 2X plus Y has to equal 60. Okay, and what else do we know? Well, we know that this angle in here is 30 degrees because this is a right angle. So, and it has to add up to 120. So let's look at our area right now and see what variables we need to represent. So we have Y times H, which gives us this middle part. And we have two triangles that are both half of the base. So we need something to represent this little. So we'll call this width, this little space here. Width times height. So, I mean, we can collect the 2 and the half. But what we can see is the problem here is that we have a Y, an H, and a W, and an H. And we're actually going to create a function that's all in terms of X. Okay, we are going to create an area function that's all in terms of this X. Okay, so is that the only variable that you can use? Not necessarily. I mean, I challenge you to try to solve this problem using a different variable. It's just that you have to represent everything with one variable. So because of this, we can say that Y is equal to 60 minus 2x, okay? So we have Y in terms of X, so that's good. So now we think about how can we represent H and W in terms of X? Well, this is where we go back to trig. Here we have a right angle triangle where we know that this angle is 30 degrees. So we can say that the cos of 30 degrees is equal to adjacent, so H, over hypotenuse, X. Sorry, that's an X. So H is just equal to X times cos of 30 degrees. And we know from our handy dandy special triangles that the cos of 30 degrees is just root 3 over 2. So height can be represented by root 3 over 2x. So we can do something similar for width, okay? The sine of 30 degrees is equal to width over x. So width can be represented by 1/2 x, since the sine of 30 degrees is a half, and we bring up the x. So now we have our width, our height, and our y all in terms of x. So all of our things are in terms of one variable. Things, very technical terms, as means, come on. So now we can start and create our function. So we'll say let A at x represent area in centimeters squared at, what should we call that? We'll call it like angled side length. X in meters, or sorry, in centimeters. Okay, so A at x equals y, so 60 minus 2x, times h, so root 3 over 2 x, plus w, so 1/2 x, times h, so again, root 3 over 2 x. Okay, and we have our function here. So what are our restrictions? Don't forget those. Sorry, I'll put a space around here. Our restrictions are x has to be between 0 and 30. Okay, since the whole thing was 60 long. All right, so now we can make this a simpler function. So you can use your algebra techniques to rearrange this. So you get 30 times root 3x minus root 3x squared plus root 3 over 4x squared. Okay, so I just multiplied those together to get that, and then I just expanded the terms to get these two. Okay, so technically root 3 and root 3 over 4, those are like terms. You could collect them, but I just left it that way because, I don't know, the roots, I didn't want to collect them. Also notice that I'm leaving everything in terms of root 3. I am not estimating. I'm keeping those true values. So now we have that function. Let's take the derivative. Okay, so this becomes 30 root 3. Okay, and then minus 2 root 3x plus, okay, so this would be 2 over 4. So it becomes root 3 over 2x. Okay, so now we want to set this equal to 0. Okay, and solve. So we get 30 root 3 minus 2 root 3x plus root 3 over 2x equals 0. Okay, now that we have this as an equation, we can do we can divide everything by root 3. Okay, just to get that root 3 out of there, that's going to make our lives a lot easier. So then we just get 30 minus 2x plus 1/2 x equals 0. Like, are you kidding me? That is a million times easier. So we go ahead and solve this, and we get x equals 20. Okay, so that means the dimensions are so that your x, so your side length is equal to 20. So that's 20 and 20, this is 40, so that you get a 20 centimeter base, and then you can go ahead and use that to find the height by putting x back into whatever you need. So it says to determine the dimensions that will maximize the height. So your x is equal to 20, obviously. So then that means that your y is equal to 20. And you can go ahead and find that means your height is equal to 17.3. And these are all in centimeters. Phew. Okay, so hopefully you understood the steps of that. Remember, it's all about creating a function in one variable, making sure that the function is what is actually being asked to optimize, and then it's all up to your algebra skills and your ability to take derivatives after that. Okay, we're going on to the next example, which is my favorite question probably that I teach. I don't know, that I teach at all, just because it's so complex and so rewarding when you figure it out, but there are so many moving parts. So yeah, so if just pause the video as much as you need to throughout this. I encourage you to really, really pay attention to what I'm saying, and just, if you need even like 2 pieces of paper to figure this out, whatever it takes, yeah, to get this example, because you'll feel very accomplished if you can do this. Now, especially because I'm going to solve this using one method, and then at the end, I'll tell you the solution manual actually uses a different method to solve it, which I'm confident that you guys can do, so that's a good challenge for you to redo this question, and I'll explain how you do it later. So this is a truck. It's going across the prairies. It's on cruise control. Let's say it's going at 110 kilometers per hour, and it's getting a gas mileage of 8 kilometers per liter. So the gas costs $1.15 per liter, and the truck loses 10.1 kilometers per liter in fuel efficiency for each kilometer per hour it goes up. So each time it increases its speed by 1 kilometer an hour. Okay, it becomes less efficient. So the driver is paid $35 an hour in wages and benefits, and then fixed costs for running the truck are $15.50 an hour. So they're planning a trip of 450 kilometers. What speed will minimize operating expenses? Crazy, right? So much is going on here. So when they're thinking about the speed, sure, it's more in fuel to go faster, but then that's less time they have to pay him. So there's a lot of stuff at work here. So we are going to break it down. All right. So we're going to break down each thing that's involved in the cost individually, and then we're going to think about the things, what is changing and what is constant. So the speed is the first thing to look at. The speed right now is 110 kilometers per hour. Okay, that's the first thing. Okay, the mileage is 8 kilometers per liter. Okay, but then they say that, but then later down we talk more about the mileage, but we'll get there. Okay, gas costs $1.15 per liter. Okay, so here we go. The truck loses 10 cents of fuel efficiency for every kilometer increase in speed. So I'm going to put that together with the mileage because that affects the mileage. So minus 0.10 kilometers per liter for 1 kilometer per hour increase of speed. So those two things go together. Okay, the driver is paid $35 an hour in wages and benefits. So that is a fixed cost. So our fixed costs are $35 an hour for wages and benefits, and then $15.50 an hour for running the truck. So those are both fixed costs, and they're both in terms of hours. So we can bring that together to be 50.5 is how much we're spending per hour, which those things together. And then our total distance is 450. Okay, so we have to think about what is affecting all of this. So what is changing? So our speed might be changing. Our mileage is changing. Okay, the gas, the price will not change, but the amount of liters we need will change. And our fixed costs don't change, but the amount of hours we need to actually operate and go this distance of 450 will change. This distance of 450 is not changing. So what affects everything? What affects everything is the change in the speed. Okay, so that is what you have to get your mind to wrap around. So it's the change in speed that affects time and cost, right? So It's the change in speed that we want to use to represent everything. So think back to our questions from before. How would you represent this variable? Okay, my brain went right to let x represent the number of 1 kilometer per hour changes in speed. Okay, because that's just what we're used to doing from these types of questions in grade 10. So now that we have that, let's think about our total costs, okay? So our speed then will be 110 plus x when we need to come to that. Okay, so it said, let's minimize operating expenses. Okay, so what are our costs here? So our costs are going to be the fuel cost and our fixed cost, which comes from the wages and the truck. Okay, and we want to represent all of these in terms of x. So let's break out, how do we come up with the fuel cost? So the fuel cost is going to be how many liters we need times the price per liter. Okay, we know that the price per liter is $1.15. That's not changing. It's this number of liters. So now we need to further go and figure out, how do we figure out how many liters of fuel we're going to use? Okay, I will tell you this, for me, when I did this, was the most difficult part of the problem. And when I'm having trouble coming up with what divided by what, I always look at the units. I know I needed a unit of liters. So I looked around and I figured, oh, if I do kilometers divided by kilometers per liter, that gives me liters. Okay, I'm going to be fully honest. I don't really understand mileage. So some of you will, some of you right away will know, well, liters required is distance divided by mileage. Duh, Mrs. Weens. I didn't know that. So I had to use my math knowledge to think, okay, what division of units will give me just L? And I looked at all the units I had. Some were kilometers, and then there was kilometers per liter. And I thought, well, kilometers per liter divided by kilometers doesn't give me liters, but this does. So I looked at the units and used that to figure out. So kilometers is just the distance, and the kilometers per liter is the mileage. So we know that the distance is 450. And okay, so we have to think about, what is the mileage? Well, right now it's $8, but it's going to be reduced by 0.1 per x, since we let x be our variable. So that is our expression there for the number of liters. So now I can go back to my fuel cost. Is the number of liters, so that's 450 divided by 8 minus 0.1x times my price per liter, which is $1.15. So I can multiply that through, and I get 517.5 all over 8 minus 0.1x. So now I can come up with my total cost function. Oh, sorry. No, now I need my fixed cost. So my fixed cost is this 50.5h. So now I need to represent my time, my number of hours, in terms of x. So remember, this is time. So remember our distance, speed, time situation here. So time, or a number of hours, is distance over speed. So this h can be represented by 450 divided by 110 plus x, because my speed is 110 and I'm changing it by x. Okay, so now I have my cost function. C at x equals 517.5 over 8 minus 0.1x plus 450 over 110 plus x. Okay, so then what are the restrictions here? Oh, sorry, that's times 50.5. 50.5. Okay, and then you can multiply that through 517.5 over 8 minus 0.1x plus 22725 over 110 plus x. So there's my function as simplified as it can be for now. I'm not going to get a common denominator because when we find the derivative and set it equal to each other, it's a lot easier without a common denominator. In terms of restrictions, I mean, x is how much you're changing speed. So I don't know, how much of a speed demon are you? Like, you don't want to go under a certain speed or over a certain speed. So we'll just, for this question, I would just write something next to it, like restrictions depend on, you know, speed limits or allowable speed, things like that. We're just going to find the answer because you'll see that our final answer is way above most speed limits, but that's okay. So the rest of it, I'm just going to show you worked out because it would be so much writing on the trackpad. So I just scanned in my solution. So I hope though that like the most difficult part of this is coming up with this function. And now you just got to rely on your ability to take derivatives, guys. So I will show this to you here. So here I take the derivative, okay? So I'm taking the derivative of this. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So I knew the derivative of the top was 0. So I just went right to the other part. So minus the top. So minus the top times the derivative of the bottom. So that's why there's only that there, all over the bottom squared. Okay, and then this is subtraction because it's the same situation. I know the first part of the quotient rule goes away because this derivative is 0. So it's minus the top times the derivative of the bottom. The derivative of the bottom is just 1. So that's why you get 22725 and then the bottom squared. Now, when you set your derivative equal to 0, these two fractions equal each other because you just move 1 over. So now you have to cross multiply, which is what I did here. Okay, after you cross multiply, you can expand your binomials, and then you move everything over, and you have one big quadratic formula question. Okay, and you get your answers of 253 and 18.6. All right, so I mean, copy this down or pause the video, see if you can work through this, how much of this algebra you can do on your own. It's doable. You just have to really think about each step. You have to be very conscious and confident in your skills in order to do this, okay? So your answer here, 253, obviously we're not going that high on our speed, but 18.6, okay, so it's saying that the speed to minimize cost is 128.6 kilometers per hour. Some of you guys might drive that. Seems pretty crazy for a transport truck, but that was the answer to this question. Okay, just wanted to show you, if you go to GeoGebra, here I put in the function, and you can actually tell GeoGebra to give you the derivative, which it does here, but you can also ask GeoGebra to solve this for you. And then it'll come up with this huge number, but you can press this little wavy thing to give you the estimation. And of course, now it's not giving it. Oh, there it did. Sorry. See, and you get 18.62 and 253, which is what we just found. So you can use GeoGebra in your verification along the way to see if your answers are right, and that might help you next year in university too to know how to use that. So a few 2-hard examples. I hope you guys were able to understand at least parts of it. Please spend some time identifying sections you did not understand so we can review it in more detail in class. So thanks for watching, guys. Hope you learned lots.